Welcome to G Fun Facts Online. Today, we're talking about the time humanity punched an asteroid. On September 26, 2022, in a control room filled with a mixture of tension and hope, scientists at NASA watched as a spacecraft the size of a vending machine, traveling at 14,000 miles per hour, slammed head-on into a distant rock. This wasn't science fiction. This was the Double Asteroid Redirection Test, or DART, and it marked a pivotal moment in human history. For the first time, we didn't just observe the cosmos, we actively changed it, all in the name of learning how to protect our own planet from a potential future threat. The DART mission was more than just a success. It was a cascade of scientific revelations that are still reshaping our understanding of asteroids and how we might one day save ourselves. So let's unpack the incredible story of what happened after we nudged an asteroid. The target for this audacious cosmic experiment was a binary asteroid system called Didymos. The main asteroid, Didymos, is about 780 meters across, roughly the size of a small mountain. Orbiting it is a tiny moonlet named Dimorphos, only about 160 meters in diameter, which is comparable to the Great Pyramid of Giza. Crucially, neither of these space rocks posed any threat to Earth. Their distant, predictable orbit made them the perfect, harmless test subjects. The goal wasn't to destroy Dimorphos, but to see if we could give it a measurable push, a kinetic impact, and alter its orbit around Didymos. Could a spacecraft, acting like a high-speed billiard ball, change the path of a celestial body? After launching in November 2021, the DART spacecraft traveled for 10 long months across millions of miles of deep space. The final moments of its journey were completely autonomous. DART's onboard navigation system had to distinguish the tiny Dimorphos from the larger Didymos and steer itself into a direct collision. It was an incredible feat of engineering, hitting a relatively small target moving at immense speed, millions of miles from home. The moment of impact was broadcast live, and the world saw the feed from DART's camera cut out as it met its spectacular end. But the real proof of the mission's success would come from telescopes back on Earth. Scientists had set a minimum benchmark for success. They hoped the impact would shorten Dimorphos' 11-hour and 55-minute orbit by at least 73 seconds. It was a modest goal, a proof of concept. What they discovered in the following weeks, however, blew every expectation out of the water. The impact hadn't just shortened the orbit by 73 seconds. It had shortened it by a staggering 33 minutes. 33 minutes! That's more than 25 times the minimum requirement for success. The kinetic impactor technique was not just viable, it was shockingly effective. This astonishing result was the first clue that the physics of slamming a spacecraft into an asteroid were far more complex and fascinating than our models had predicted. It opened up a whole new set of questions, and the answers have been pouring in ever since, painting a complex picture of what Dimorphos is really like. The final images DART sent back just moments before it was obliterated gave us our first tantalizing glimpse of Dimorphos' surface. It wasn't a smooth, solid object. Instead, the camera revealed a landscape covered in boulders, rocks, and loose debris. Post-impact analysis has confirmed this initial suspicion. Dimorphos is what scientists call a rubble pile asteroid. It's not a single, monolithic rock, but rather a loose collection of cosmic debris, a gravitational conglomeration of countless smaller rocks and dust, all held together weakly by their mutual gravity. This is a common feature among asteroids we've visited up close, like Bennu and Ryugu, which were explored by other space missions. This rubble pile nature turned out to be the secret ingredient to DART's oversized success. Think about it this way. If you punch a solid brick wall, you might leave a dent or a crack. But if you punch a loosely packed bag of gravel, the entire bag will deform and gravel will fly everywhere. That's essentially what happened to Dimorphos. The impact didn't just carve out a simple, neat crater. It caused a global deformation of the entire asteroid, sending a shockwave through its loose structure. And this leads us to perhaps the single most important discovery from the DART mission: the unexpected power of the ejecta. Ejecta is the scientific term for all the material, the tons of rock and dust, that gets blasted into space from an impact. When DART hit Dimorphos, it was like a cannonball hitting a sand dune. The spacecraft itself delivered a push, a transfer of its own momentum. But the real force came from the recoil of all that material being thrown out in the opposite direction. It's Newton's third law in action on a cosmic scale. For every action, there is an equal and opposite reaction. The plume of debris streaming away from Dimorphos acted like a powerful, temporary rocket engine, giving the asteroid a much greater shove than the spacecraft's momentum alone could have provided. Scientists measure this effect with something called the momentum enhancement factor. A factor of 1 would mean the push came only from the spacecraft. DART achieved a momentum enhancement factor of approximately 3.6. This means the impact was about 3.6 times more effective at moving the asteroid than if Dimorphos had simply absorbed the spacecraft without kicking up any debris. This is a profound discovery for the future of planetary defense. It suggests that to deflect a potentially hazardous asteroid, we might not need a massive, heavy spacecraft. A smaller, lighter, and therefore cheaper and easier to launch spacecraft could be sufficient, as long as it hits a rubble pile asteroid in a way that maximizes this ejecta recoil. But the surprises didn't end there. The impact didn't just create a cloud of fine dust. It unleashed an entire swarm of boulders. An Italian space agency CubeSat named Lycia Cube, which had hitched a ride with DART and was released shortly before impact, flew past the crash site to survey the immediate aftermath. Its images were stunning. They showed not just a bright plume, but distinct streamers of boulders, some several meters in size, moving away from Dimorphos. Recent studies analyzing these ejected boulders have shown they carried away a significant amount of momentum, contributing yet another kick to the asteroid's deflection. The way these boulders were ejected wasn't random, either. They appeared in clusters, hinting at a complex interaction between the spacecraft and the asteroid's surface. Some researchers have even put forward a fascinating theory that DART's large solar panels, flanking the main body of the spacecraft, may have slapped some of the larger surface boulders moments before the main impact, helping to dislodge and fling them away in these unique patterns. The combined force of the impact and the violent ejection of material was so immense that it completely reshaped Dimorphos. Before the impact, simulations suggest it was likely a relatively symmetrical object, something called an oblate spheroid, kind of like a slightly squashed ball. After the impact, it became a more elongated, watermelon-shaped ellipsoid. The numbers are staggering. Scientists estimate that while up to 1% of the asteroid's total mass was blasted into space as ejecta, a shocking 8% of its mass was actually moved and redistributed across its surface. Material from deep inside the asteroid was dredged up and settled elsewhere. The very landscape of this tiny world was rewritten in an instant. Even its orbital path around Didymos was altered. It didn't just get smaller. It changed shape, going from a nearly circular orbit to one that is now slightly eccentric or oval-shaped. DART didn't just nudge Dimorphos. It fundamentally re-engineered it. The wealth of data from DART will keep scientists busy for years, but the story is far from over. To truly understand the long-term consequences of the impact, a follow-up mission is on its way. The European Space Agency, or ESA, is preparing the Hera mission, scheduled to launch in October 2024. Hera will arrive at the Didymos system in 2026 to conduct a detailed crime scene investigation. Its job will be to meticulously survey the aftermath. Hera will precisely measure the mass of Dimorphos, which is a crucial variable we can only estimate right now. It will study the properties of the impact crater, which we've never seen, and analyze the asteroid's composition and internal structure, Hera won't be alone. It will deploy two small CubeSats of its own, named Milani and Juventus, which will perform close-up inspections and radar soundings to peer beneath the asteroid's surface. The data gathered by Hera is essential. It will allow us to validate and refine our models of kinetic impacts, turning this incredible one-off experiment into a well-understood and repeatable planetary defense technique. There's even a small but tantalizing possibility that when Hera arrives, it might be able to spot some of the larger boulders that DART ejected, still lingering in orbit around the binary system, a lasting monument to the impact. The kinetic impactor, so brilliantly demonstrated by DART, is now our most mature technology for asteroid deflection. But it's not the only tool in the potential toolbox. The best method to use would depend entirely on the specific threat, the asteroid's size, its composition, and most importantly, how much warning time we have. For situations where we have decades of notice, a more gentle approach might be preferable. One such method is the gravity tractor. This involves parking a heavy spacecraft alongside a threatening asteroid and simply letting its tiny gravitational pull slowly tug the asteroid onto a new, safe trajectory. It's slow and steady, but highly precise. Another technique being explored is laser ablation. This would involve using powerful lasers, possibly from multiple spacecraft, to heat a spot on the asteroid's surface until the rock vaporizes. This jet of vaporized gas would act like a small, continuous thruster, gradually pushing the asteroid over time. And then, of course, there is the last resort, a nuclear detonation. The goal here would not be to shatter the asteroid, which could dangerously create multiple, unpredictable threats. Instead, the plan would be to detonate a nuclear device at a carefully calculated distance from the asteroid. The immense energy and radiation from the blast would vaporize the surface, creating a massive, powerful push to shove it off course. All of these concepts, from the gentle to the extreme, will be informed by the real-world data from DART, which highlighted just how critical it is to understand an asteroid's physical properties before you try to move it. The DART mission has pushed us into a new era of planetary defense. We have officially moved from theoretical concepts in Hollywood movies to a proven, practical capability. The threat of a catastrophic asteroid impact, while low, is real. But the success of DART shows that we are not powerless against the random mechanics of the cosmos. For the first time, we have taken a concrete, physical step towards being able to protect ourselves. It was a mission born from ingenuity, international collaboration, and the courage to take on a challenge of cosmic proportions. The legacy of DART isn't just a new crater on a tiny, distant asteroid. It's a new sense of security and a powerful testament to what science can achieve in the service of humanity, ensuring that we can safeguard our only home for generations to come.